This video is going to do calorimetry problems which are found in Brown LeMay in section 5.5. This is Mr. Sitta. I'm going to start off with some of the notes that are listed, and down here we're starting section 5.5, which I've kind of separated for you on the notes. Specific heat capacity. Okay, when I say what's heat capacity, that's how much heat, in real words, it's how much heat a substance can hold. So you might ask yourself, like you're cooking and you have a glass bowl and you might have an aluminum foil sheet. Well, you could ask yourself which one holds more heat. And if you experience the kitchen a little bit, you'll find out if you take pizza off an aluminum sheet, the aluminum sheet will get hot real quick and will get cooled down real quick. So metals tend to have a low specific heat. They don't hold a lot of heat. Okay, glass. A painful lesson is to find out that you go to grab the glass and you find out that the glass takes a lot longer to lose its heat. It will stay hotter. So what that means is it has a higher specific heat. If you heat the glass up, it takes longer to heat than the metal, and that's all expressed as specific heat. If you're living down the shore in Ocean City, you experience specific heat all the time. It's part of what makes people want to live down the beach. Okay, reason being is water has a very high specific heat, but water is used as the standard specific heat for everything. If we use it in calories, the specific heat of water is 1 calorie. But being that it's very high, as it gets hot in Philadelphia and you're in like July, it might be like a 95-degree day. Well, if you come down the Jersey Shore, because that body of water, first of all, it has a lot of mass, but specific heat, it holds a lot of heat. So sometimes we call that a heat bath. Okay, they use those in computers. They might have a big hunk of copper that's used as a heat bath to absorb the heat from the computer. Well, your ocean is your heat bath. So if you come down the shore in July and it's 95 degrees in Philly, it still might be like 84 degrees in Ocean City, because all that heat from the air is going into heating up the ocean. And so it stays cool during the summer. Well, by the time September runs around, the water's gained a lot of heat, and now the water's holding a lot of heat, which it's going to release very slowly. So as it starts to cool down in Philly, you might get October and November days when it's very cold in Philly. But down the shore, they call it Indian summer because the ocean's still releasing its heat. And so you'll get some really nice days in October and November, and that's all due to the specific heat of water. Specific heat, okay, CP is the C is your letter for specific heat, CP. Okay, it's the quantity of heat transferred. The top is joules, divided by the grams, divided by the temperature. So when I say the specific heat of water, it means 1 calorie per 1 gram per 1 degree, and that's 1, the specific heat. If I put that into joules, it's going to be 4.184 joules per gram per degree Celsius. That's the CP of water. Now, heat capacity, the energy to raise a temp by 1 degree. What's missing here, when you say heat capacity, that really depends on the number of grams. So if I have like the ocean, that has a high heat capacity, because you're not just saying 1 gram, you're saying how many grams you have. So it's just totally, it's kind of totally the number of the mass that you have. If you turn that mass into moles, then you got yourself a molar heat capacity, joules per mole per. Now, this is interesting. It's temperature change. In the world of temperature change, it doesn't matter whether you're Kelvin or Celsius. Meaning that if you have boiling water and boiling water is 100 degrees Celsius and freezing water is 0, then the delta T for that is 100. Now that can be in degrees Celsius. Well, if I turn this into Kelvin, this would be 273. This would be 373. But they're on the same scale, so your delta temperature could also be in Kelvin. So it really doesn't matter whether you have Celsius or Kelvin if you're looking at delta T, the change in temperature. Okay, let's go on to calorimetry. And calorimetry can be taught, that can be taught in grade school. Not a real big issue, okay? Calorimetry is the study of heat, okay? Today we call, our chapter is thermochemistry. In the 1800s it would be called caloric theory. The caloric theory was studying heat, okay? Here's our one equation that we want to use for calorimetry. Q equals Cp times M times delta T. This stuff is fresh fish. We're just plugging into this equation, solving for one of four variables. Q is your amount of heat, and normally we would measure that in joules. We're not really going to use calories. Okay. M is the mass in grams, so this is not SI, Scientific International. Delta T is your final minus your initial temperature. Okay. I tend to look at this as absolute value. I tend to just say, I look at the change in temperature at the end of it to see if it goes up or down. And then specific heat, that would be the specific heat of water usually. So water, the Cp of H2O is equal to 4.184 joules per gram per degree Celsius. And usually we're just going to use degrees Celsius, not Kelvin. And this little down here tells you that the heat lost by a substance is equal to the heat gained by a substance. So if you have a reaction where the heat is lost is negative, then it's equal to the heat gained by the solution. Usually when we do calorimetry, what we do is we take a glass of water and allow the reaction to pass the heat to the water, and being that we know our Cp of water, we can then find the Cp of we can then find the heat from the reaction. Okay, so let's look at some of these problems, which are fairly simple. Okay, this work's been posted online, so this will kind of be your solutions to the work that I'm posting online. And my cell phone is moving slowly. Try and secure everything here. Okay, I think I got it. And I just have to peek and see that I'm set. Okay, here we go. You always have examples up top, which are really nice. But let's just go and do exercise 6. How many joules must we remove? So Q equals question mark joules. To lower the temperature of mass equals 18.5. As usual, I'm just going to create a list to make my life simple. The delta T. Okay. Now you're removing heat. Okay. So your change in temperature is going to be negative because you're taking heat away. So I'm going to go from, it really doesn't matter, I'm just going to say 46.4 minus 22.4. Okay, so I'll just look at the absolute change in temperature, and that's going to be 24 degrees Celsius. So that's my change in temp. Okay, the specific heat of water, Cp, equals 4.184 joules per gram per degree Celsius. Okay, and then it wants you to find Q. So easy as pie. Q equals Cp times M times delta T. Okay, and then Cp is 4.184 joule per gram per degree Celsius. times the mass, 18.5 grams, times the delta T, 24 degrees Celsius. So my Q is 1860 joules. Now, like I said, I don't put negatives and positives on this, okay? So you have to remove, or I'll say absorb, from the water. So if I want to put a temperature on it, because this temperature is going down, I can put my negative there and just say that's a negative amount of heat. And that's how you do the problems. They're easy. To me, I always look at absorbed versus released. Okay? So this has to be absorbed from the water. If I drew a picture, my heat's coming out of the water. So my delta H is going to be negative. It's going to be an exothermic process releasing that heat. Gosh, I wish this fan had stopped moving. That's going to be my problem. Okay. Next one. Same thing. I got Q equals 73.51 joules. Thing to check, always watch your units. If they throw kJs at you, you have to make a conversion, which they will. M equals mass, 25.6. Now, it says what would be the final temperature. Now, here's where I don't mess with this. I just say find delta T. I don't like to get fancy and put my numbers in. It gets very confusing. So I'm going to just make it simple and solve for itself. CP is 4.184. I told you you'd get used to that number because you're going to be using a lot. Okay, so I set my equation, Q equals CP times M times delta T. Well, I'm going to make it real simple. I'm just going to solve for delta T. Delta T equals Q divided by CP divided by mass. CP over mass gets delta T, so I'm going to have CP over M. Okay, plug my numbers in, 73.51 joules. The mass, the CP, 4.184 joule per gram per degree Celsius. Joules cancels out, and grams is on the bottom, 25.6 grams, and grams cancels out. So, he didn't give me an answer. 73.51 divided by 4.184 divided by 25.6. That's 25.6, huh? Okay, the change is 0.686. So I'm really just going to round that off to 0.7 because I can see I got that. Degrees Celsius. Okay. Now it added heat. So if I know I added heat, I know my delta T went up. So it's positive. Okay. So the change in temperature, I know the change in temperature is 0.7. What's going to add to the 25.3? Okay, because the temperature is going up. That's why I say I don't make this confusing. Try not to. The answer is 26 degrees is your temperature final. And like I say, I always just look at it and say, is the temperature going up? If the temperature is going down. If it is heat added, then the temperature is going up. Then I add the change of heat to the temperature. If the temperature is going down, then I subtract. Simple. Another concept, negative Q equals positive Q. Well, this gets me into the fact that I can have Q1 equaling CP times M times delta T. And I can have a separate amount of heat equaling CP times M times delta T. Okay. And Q1 will equal Q2 but they will be opposite signs. If one's a positive, the other one's going to be a negative. Or if the other one's a negative, the other one's going to be a positive. But the fact is, I can set them equal to each other. So let's try one of these problems. They have an example right here, and so I can always take these two and set them equal to each other to solve problems. And this is calorimetry. And one thing you always want to do on these, draw a picture. Pictures really help you, okay? Help you understand. I guess this is the same problem. How many joules of heat? Q equals question mark joules. Mass equals 18.5 grams. Delta T, the difference, 46.4 minus 22.4. And so this is 24. Okay. I feel like I've done this problem. Yeah, I have done it. Okay. Sorry. We're going to do the problem on the back. Alright. An 18-gram sample in 98 is added to a glass of water, so I'm going to draw a little picture up here. Here's my glass of water. And here's a bar of copper. I'm going to add that copper to the water. Okay? So when I look at my copper and I look at my water, heat's going to go from one to the other. Okay? Now, let's look at the copper. The mass is equal to 185 grams. The temperature is 98. Temperature initially is 98 degrees Celsius. Point out. Okay. I add it to, now here's the water. So I'll put the water on the other side of the world. The mass of the water equals 102 grams. And the temperature initially is 20. In a perfectly insulated calorimeter, the final temperature of the copper, so TF is equal to 31.2 degrees Celsius. So TF equals 31.2. The temperature for both of them ends up being 30. Calculate the specific heat of copper. I know one more thing about water. I know that the CP of water equals 4.184 joules per grams per degree Celsius. Now I can find out the delta T for each of these. Okay, the change in temperature of the water is 31.2 minus the 20, so it's going to be positive 11.2 degrees Celsius. That's delta TF, delta T. Okay, the delta T over here is going to be 98 minus 31, okay, and it's going to have gone down, so this is going to be negative. Okay, so I got 66.8 degrees Celsius. All right, I don't know the CP of the copper, so what I know is that the Q of the copper equals the Q of the water. Okay, the Q of the copper was negative, the Q of the water is positive. Okay, so what I can say is I can say, well, for copper, CP times M times delta T equals CP of the water times M times delta T. I could look at that as a transitive property where I have one equaling the other. Or I could solve for the Q and then plug in the Q. So I can solve for the Q of the water. So there's two different ways I can do this. Let's just solve for this. 4.184 joules per gram per degree Celsius times the mass, 102. So grams cancels, times temperature, 11.2 degrees Celsius. That cancels out. That's Celsius. So I get 4.1184 times 102 times 11.2. Okay, this equals I'll say 4780 joules. Okay, so that's equal to your Q. Well, that's equal to the CP. And what I'm going to do to solve this is I'm going to divide this M times delta T. So I'm going to divide this by the mass of the copper, 185 grams, divided by the temperature change of the copper, 31.2 degrees Celsius. So the CP of the copper equals that, now divided by 185, now divided by 31.2. So I get 0.828 joules per gram per degree Celsius. And I get the wrong answer. 98.1 minus 31.2, 66.9. It's not that big though. It's 185. 102, 11.2. Try that again. Divided by 185, divided by 66.9. Oh, I don't know what I did. Second time, I come out with 0.39 joules per gram degree Celsius. I just think the button didn't click right. Okay, very good. And that's how you do these problems. You're always going to set up the one substance here, the one substance there, and you can actually take two different volumes of water and combine them. I'll try doing number 10 because that's that one. 9 looks like a repeated last equation. Okay, what is the final temperature when? This is a little different. I have 2 cups of water, and I'm going to put the water together. So I'm going to add this water to that water. So this will be my cup number 1. Okay, I have volume equals 150. Temperature initial equals 90. And then in this one, cup number 2, and you notice they're giving you milliliters, 100 milliliters, and I'll tell you what to do with that in a second, and 30, and that's my T initial. This is going to be turned into a mass. Water is 1 gram per milliliter, so I can just say times 1 gram per milliliter. So this can be considered to be 150 grams. So this water has 150 grams in it. This water has 100 grams in it.